Okay, my wonderful students, let's begin lecture. Couple things I want to go over with you. If you came in a little bit late and we already passed your name in the handing back exam printouts. How do you look? Pretty good? Still's not picking it up. Dude, you ready? Yeah. You ready? Yeah, good. All right. Couple things. If you were a little bit late getting and you didn't get your printout, we'll catch you at the end of class on the way out. We'll probably dismiss a little bit early today. Second thing, and this is to reinforce something that I've mentioned before, on these printouts, the percentage that's on there is not accurate because your grade is based on the clicking as well as the Scantron. Now, the raw score on the printout that you just got is accurate, right? Third, I want you to look everybody at your printout real carefully and see if you have a blank or if you have an item that has two answers, because two answers will be considered incorrect. And blank, of course, will be considered incorrect. Now, if you have those, I want you to bring those up right now and give them to Miss Caroline. All right? If you don't have them, just, that's good. But if you got one, what do you have, a double? Yeah, come on, bring it up. Blanks, doubles. It won't be many of you, but if you do have one, bring it, and that'll be helpful. And we'll get it squared away and give this back to you. Give it to Caroline. Okay? We'll get these all sorted out for you and see if you really do have a blank or if you two answers or one answer. Good. I'll take all these. Okay, another comment. Because of some technical difficulties, we're not going to be doing any clicking today. What, did you forget your clicker? I just saw somebody in the back go like this. That's good. I'm glad you bless yourself in the middle of class. Every minute of every day is appropriate for that. I've never seen that before. Anyways, we're not going to, the clicker machine is not working. So I have clicker questions, and you can jot them down like you're jotting down notes, and we'll talk about them as we go. Speaking of clicking, I want to go through an example of generating a clicking grade, something out of 25 possible, for somebody that's below the 85% performance level. All right? Now, the way that you start is by looking at your grades page. Specifically, you look at the latest summary, which was March 3rd, and you look at the one marked answers. That tells you how many clicker questions you actually answered. All right. Now, right now, the baseline until Thursday is 28. We had another 4 planned for today, but anyways, right now on the books there are 28. So this student, this imaginary student here on display, has got 24 answers out of 28 questions. All right? And so, and that's right here in this 24. Now, let's go ahead and put together the actual grade for this student, and then for another student that does a little bit lower level performance. Here we go. As you know, the clicker questions total right now is 28. And that means everything from the first official day, which I believe was January 31st, up until March 2nd. That was lecture 16. All right? Your 25 out of 25 participation grade is based on, I mean, if I was going to give it today, it would be based on 28. So if you, in other words, if you have 85% or more, you get 25 out of 25. And that gives you a little bit of leeway to miss 1 or 2 lectures. All right? Because 85% of 28 is 23.8. Now you can't answer 0.8 of a question or a tenth of a question, so we would just go to 24. So if you've answered 24 questions or more, then you're golden. You got 25 out of 25 right now, today. Now, we're going to be asking more clicker questions through the semester. We're going to have a ton of them. And so your pointage will change. But if today you have 24, you're good. 25 out of 25. All right? So this student, in this example, gets 25 out of 25. And, you know, we've had lectures where we've only answered 1 question. And we've had lectures where we've had like 10 questions. So it just depends which one you miss. But usually 1 or 2 lectures, if you, you know, like I say, if you have to go to the dentist or your roommate's car got stolen or whatever reason, you have to ditch 1 or 2 lectures over the semester, you're usually okay. Camille, question.
So we look at the correct, and then can we add the 5 points from the beginning, the extra credit that we get for having our tutor early? Or does that already add?
The correct number that's also in the grades page goes into extra credit at the end of the semester. And that's one where you want to have 75% correct. And in this case, this guy just makes it 21 out of 28 is 75%. So if I was doing semester grades today, this student here would get 4 bonus points, okay? And then those go in on top of all your regular points. Now, we're just going to be doing regular point grades today, but I'll mention how the bonus points are handled at the very end, okay? All right, anyway, so this student gets 25 out of 25. And that, my wonderful students, is a nice chunk of change. Now, let's do a hypothetical second case. And let's say that another student, John Q. student, answers only 17 out of the 28. You know, he forgot to come to class. He was abducted by aliens another time. And his roommate's mother-in-law's cousin stole his clicker. So he only has 17 out of 28. All right, so now this is the proportion. Go ahead and write this down. This is actually part of your clicker question. So make this part of your notes for John Q. student. Let's say that he has 17 out of 28. Now he's got to solve, and you've got to solve this proportion. In the numerator on the left side, his performance percentage, 17 divided by 28. And we'll calculate that in just a minute. Get your calculators out as well, just for safety. In the denominator, the baseline of percentage, 0.85. Now, over on the right, the numerator is going to signify his pointage. So this is going to be a number somewhere between 0 and 25. All right? And in the denominator, the max possible pointage, 25. All right? So that's the proportion that you've got to solve, or that this student has to solve, and we're going to solve it together right now. Okay, the numerator, 17 over 28 is kind of stinky, 60.714%, or 0.607 0.714. So that's the numerator over there on the left side. All right. Now, we haven't done anything on the right side yet. And we haven't done anything with the denominator, but we've got the numerator, calculated out. Okay, divide that by 0.85. If you have your calculator, if you put down your Cheetos and take out your calculator, you'll be able to You'll be able to verify that 0.60714 divided by 0.85 is 0.7143. All right, so that's the next thing. So you're doing it on your calculators. You're eating Cheetos and you're doing calculations, and this is what it comes out to. All right, now that's the left side. Now we still have the right side, and that's where the pointage is. But we've got to get the pointage by itself. And how do we do that, Elizabeth? By cross multiplication. All right, can you see it? Can you see the cross multiplication? Because you're going to do it in about 2 seconds. But since we don't have clicking, we're just going to take notes. So make a note. Calculate the participation pointage. There's your proportion. And now cross multiply to get the pointage level. All right? So take your calculator out and actually try to do that now. Well, what does the syllabus say? Right, I always round it up. On this calculation, and also for homework. Another one sneaks out. No clicking, they sneak out. I think I'm not looking. Okay. The answer, let's figure out the answer here. I've got it laid out. Here's your cross multiplication. 0.7143 times 25. And that'll give you your pointage. And hey, you guys, that works out to 17.8575. Raise your hand if you verify me on that. Okay, good. And then what I always do is I always round up. So this particular student would actually get 18. Okay? Simply because at the end of the semester, I don't want to be dibbling around with fractions of points and fractions of percentages. I just want to have a number of points, so I always round this one up to the nearest whole number. All right? So 18 out of 25 for this particular student. Now, let's put together a complete grade for the second student. And the reason we're going to do this is because I know a few of you are thinking, well, maybe I should take a W in this class because my grades are a little bit stinky. Well, I want you to do your grade calculation from your numbers after class and then decide about that. Now, most of you are doing fine, but I know some of you are nervous, so let's do a full exam calculation. So let's say that for this same student that we just did the participation points, let's say he's got 2 exams, and they're no great shakes. He's got a 27 on exam 1 and a 31 on exam 2. All right? Now, the total of that pair of exams is 58 out of 100. And if I were to do exams only, that would be a D. That's less than 60%. 60% or higher is where we get a C. All right? So if I'm down there at 58%, that's a D. But that's not the only thing that we have. We have participation. Bing! And this guy's got 18 out of 25. All right, now we just did that. Now I want to do his homework. And I'm going to give you his hypothetical performance on homework. We'll see how that stacks up. All right. Now let's say that he's in our class, and for us, from homework 1 all the way to the mini review. Remember we had that right before the test. We had a regular homework and a mini review, and they were really tough. And you guys were really working hard on those. A total of 156 points was possible. And let's say, let me remind you, homework 0 doesn't factor in. That was our attendance homework, okay? And as I recall, it was like a Chuck Norris question or something like that. So, yeah, and you had like, I said it's about 90 different attempts, so it was impossible to not get points on that one for that Chuck Norris question. Anyways, homework 0 doesn't factor in. So that was just a 1-pointer. But homework 1 through the mini review, yes, 156 points. Okay, now let's say that this guy's got 111 out of 156. All right, now that's 71%. And again, 71% for homework is pretty low. Most of you guys that are here today are going to have a way higher percentage on that, on homework, and you're going to have a way higher percentage on participation. But so this guy's kind of like he's not a really bad case, but most people are going to be above this. Anyways, let's figure out his. And again, this was supposed to be a clicker question when I thought my clicking machine was going to work. But here's what we got. Figure out, now this one, I don't want you to round it off. Just figure out the raw number percentage, 71.154% of 25. Because that's all you do for homework. So you figure out, so you might have 129 out of 156. Okay, that's a different percentage. But this guy has 111, right? You might have 156 out of 156, and many of you will. In that case, cling, 25 out of 25. But this is for the case where, okay, you're not quite, at the 25 out of 25 level, but what do you have? All right. Let's see if you guys verify me. Anybody verify me? 17.7885. Okay, raise your hand if you verify me on that. Okay, good. All right, so that's the normal thing. So I just wanted that number. And when you're, tonight when you're saying, let me see what my grade is, you'll get a number like this. And then don't forget, though, you round up. And so that would be actually in the grade, if I were doing grades right now, I'd enter that in my grade book as 18. All right. So let me pause for questions about clicking and homework. Yes. I'll factor in the extra credit points at the very end. And Camille, don't let me forget to go over it. Okay, so what is your name? Jennifer what? Okay, Jennifer Gibson, Camille Robinson, do not let me forget to mention bonus points. Question over here.
How many more homework points and clicker questions?
For the semester? The question is, how many more homework points, how many more clicker questions for the semester? I do not know. A ton. That's all I'm going to say. Okay. It's going to be, we've already got 156 homework. So, it's going to be over 200, maybe even 300. Just depends. All right. But whatever it is, this is how you calculate it out. And you can do this at any time, after every homework and after every update of the clicking answers incorrect. All right. So let's get back to our calculation. All right, so this guy's got 111 out of 156, and that gives him 18 out of 25 for his homework pointage. Now, that's the one we just calculated. All right, now we're going to figure out his grade, and this is according to the syllabus. And by the way, if you haven't downloaded the syllabus, the new corrected version, it's in PDF on the website. Anyways, his total pointage, regular points, is 94 out of 150. So that's 58 from 2 exams, 18 from participation, and another 18 from homework. All right? Now, what I'd like to point out to you is the following. The homework and the participation grades add up to 36 out of 50. And this particular student, it's hypothetical, I just made it up, but this particular student has a grade of 36 out of 50 on the grade book, and that is the equivalent in his grade calculation of an exam on which he got 36 out of 50. And that is nice because he doesn't have an actual exam. He hasn't hit 36 yet. The highest he's gotten is 31. Now, hopefully exam 3, he'll have 36 or higher. But for right now, that's helping his grade. And you can see it now in the pointage, the total pointage, 94 out of 150, because that works out to 62.67%. And that would be a letter grade of C, according to our syllabus. Now, here's the grade scale. Here's a close-up of it. All right? And until the final exam, you have to go by the percentage column. So this particular student is looking at a C, even though his 2 midterms average out less than a C. And he hasn't done he's not great shakes on homework, and he's certainly not great shakes on clicking, but he clicked just enough and did just enough homework to snag a C instead of a D. Let me pause for questions. Jennifer and Camille, let me pause for questions. Okay, what about the 5 extra credit points? Now, right now, we've got early iClicker registration bonus, and we will have other bonus points coming in at various stages, mostly toward the end. Like when we get SSG bonus points and stuff like that. Now, here's where those would come in. They're not on the screen here. I normally just do regular calculation because it's the most conservative estimate of a grade until the final exam. But you can mentally add in any bonus points you have. So if this guy had 1 bonus point from early iClicker registration, you know where it would go? It would go right here. Let me get my cursor. Ooh, I didn't make my cursor gigantic. It would go over in the 94 over 150. It would go in the numerator. So he'd have 95 in the numerator, but no change to the denominator. So that's what bonus points do. The only effect they have is in the numerator, and it's only to go up, never down. There's never a negative bonus point. Not in my class anyways. I've heard of some instructors, they give you attitude points. Have you ever seen, I've heard about it in high school, attitude points. But that's heinous. I never do that. If you have the worst now don't get any notions. But if you had a bad attitude, I'd still give you the same grade as if you had a normal attitude. I never give attitude points. All right. So, Jennifer, does that answer your question? Camille, good? All right. Question over here somewhere? Yeah. Lexi.
Can you just go over again how you got 94 out of 150?
Yeah, 94 out of 150 is exams, total of 58. 58 plus 18 is 76. And then another 18 from homework. See that in 3C? Okay, so that's 76 plus 18, 86, 94. Okay, so that would be, now if he didn't have any bonus points at all, Lexi, that would be his, and if it was the end of the semester, that would be his grade. But, we've got more homework coming, so his homework pointage can change, hopefully upward. Same with clicking. And also, students, let me remind you, We also have another big change in the grades coming, and that's exam 3. Once exam 3 is on the books, then we do this nice little maneuver of keep the best 2, drop the lowest. And for many, many of you, that will bring your grade up. All right? If you have, 1 stinky grade and 2 decent grades, we'll drop the stinky one and keep the 2 decent ones, and that'll bring your average up nicely. Okay, so we've got stuff still ahead of us. Of course, we have the final. That's a big one. Right? So this is, as I say, this is an estimate of where you are right now if I were giving letter grades today. Question over here. Bonus points? Yeah, to the numerator down there at the bottom, 94. So if, like I said, if he had 1 bonus point only, like from early iClicker registration, then that would make him 95 out of 150. And so it would change his percentage a little bit, So I never do, when I'm working with students, this, second half of the semester, everybody's always starting to think about grades and stuff. I always do this much, and then I say, you look after your bonus points. If you've got any, add them to the numerator, or just kind of mentally add them in and know that whatever I've done here with you, like this one, you're actually a little bit higher if you have any. Any bonus points that you can get will bring this up, a little bit or quite a bit, depending on how many you get. Another question. Somebody else had a question. Ashley.
So if you get invited to do the special study group leader, how does the final go on the course then?
In front, a question from Ashley. If you're a special study group leader, how does that affect the grades, the final exam? If you're excused from the final exam, you're excused. So that means that for the special study group leader that does everything they're supposed to do, and they get excused from the final, their grade for the semester is based on 150. And it will look a lot like this, except they'll have 3 midterms. And so they'll have, best 2 out of 3. But they'll have homework and clicking, and then they just won't have the final. If they qualify. All right, another question. Yes.
What chapters will exam 3 be on?
Exam 3 will be on chapters 7 through something. I can't tell you. It depends on how fast we go. But we're going to be in 7 today. We'll get you organized and stuff. But I can't see that far ahead. I'm not that smart. Oh, one more thing I want to mention. For those of you that are thinking, I think maybe I've got enough grades to be a special study group leaders. Here's how it'll work. I'll look at the grades, the exam 1 and exam 2 performance, and then based on that, I'll send out invitations to a set of students, and I never know who it's going to be or how many. It's never enough. I always like to have more, but it'll be a decent number, and those students will, and I'll send out an invitation, and I'll spell out what the obligations are, what you've got to do, and then, of course, your reward, which is to be excused from the final. And then those students that get an invitation, they'll say, yes, Dr. B, I'd like to, or no. And you're not required to be an SSG leader. If you can't fit it, if your schedule is totally booked 24/7 for the next 3 months, I understand, it happens. And every semester we have 1 or 2 students that I invite that say, no, Dr. B, I just can't get it into my schedule. If you're an ed major or any kind of professional, though, it's very, very good to A, to have on your resume, B, to get recommendations from, and C, it's very good experience for a professional to be leading small groups, because that's how you become a leader in big groups. So it's good if you can do it, but you're not obligated to. So, and I don't know who here in this room is going to get an invitation, but if you do get an invitation from me, it'll be in Web Courses messaging. It'll all be spelled out what you have to do, but you have to agree or not, or say, no, I don't want to do it, Dr. B, and then we'll go from there. Okay, so that'll be coming up in the next week or so. Question?
For a student who got like an A on the first exam or a really high B on the second exam, would you still consider them?
Yeah, it depends on what your total is, your average out of 100. So I'll be looking at them closely. We'll just see, and I haven't done it yet. So they're not even published on Web Courses yet. So so it'll take time, but in the next week or so, I'll be sending out invitations probably. And then special study group leaders will run a special study group for 6 of their classmates before exam 3. So between the Thursday and the Tuesday of the exam, the Thursday, the last lecture, and the Tuesday of the exam, you'll figure out a special time and place for your special study group, and then you'll do it again right before the final, during finals week. Okay, last thing I'd like to mention on this slide is that if you haven't already noticed it, there's a correction on the syllabus, and since it's now in lecture, you're all officially informed of it. The typo on the original handout was 178. It should have been 188. Okay, and that's in one place only, the point value for letter grade B for the semester. All right? And so the PDF that is now downloadable, you can ditch the handout you got from me on the first day and download the new PDF, and you'll be at just this one change right here, 188 instead of 178. Okay, let me pause for comments before we continue.
How much including of exam 3 are we going to continue to work on the materials and can we have that?
After exam 3, yes, we will be continuing. We'll have about a week and a half of new material. So so there will be some new stuff on the final. Another question or a comment? Yeah, the guy that wasn't even paying attention, he's already left. It's it's a free country. You guys are paying for it. Sometimes amazes me what the decisions that are made by students. Anyways, let's take a look at waves. And we're going to start Chapter 7 concepts today. Now, look at this wave. This is out in Maui, in Hawaii. North coast of Maui, probably in the winter. Oh my goodness. Raise your hand if you surf. Anybody? One person? Couple? 3? All right. I venture a guess that you've never even surfed on even a wave half that big. Now look at this guy. This is in Portugal. Praia do Norte in Saint Nazaire, Portugal. Oh, and see this little dot down here? Right in here? That's a guy on a surfboard. And the wave's starting to break. I tell you what, those guys, now look at this. Same place. Oh my goodness. Can you imagine the rush? Oh my goodness. See, because if you go to Saint Nazaire, they've got a beautiful beach. And then behind the beach is a cliff. And on top of the cliff is this house. And those guys are on the roof of the house. And they're just barely looking across at the peak of this wave. It's a big mother wave. This guy, and he's halfway down it. Oh my goodness. And it turns out that there's an underwater canyon that when the waves come in at just the right angle and just the right amplitude and everything, they make gigantic waves like this one at Saint Nazaire. Oh my goodness. Now, the reason that we're going to be studying waves is so we can understand the basics of surfing, but also because waves will be an excellent way for us to understand. Excuse me. Every day in lecture at about getting close to 1 o'clock, I always sneeze. I don't know why that is. It's probably that music class down on the first floor. The reason that we want to study waves in chapter 7 is because with wave concepts, we'll be able to understand the quantum world of atoms and molecules. Now, that's in deeper chapters in the textbook, 8 and 9 and so forth. Okay? So the quantum structure of atoms and molecules, Sir Isaac Newton would not have been able to hack it. The people in the 1800s, they couldn't hack the structure. They couldn't savvy the structure of atoms and molecules. They started to find it, but nobody had an idea of why it was so until they started thinking about waves. With that is one of the constants of nature. We've already talked about several. One of them being gravitational constant, capital G, Newton's constant. But for understanding the quantum world, you have to use Planck's constant. Symbol lowercase h. And my wonderful students, Planck's constant is an interesting one because it is part of every physical action and interaction in the universe. And so I always like to say about Planck's constant, it is the one constant that rules them all. No interaction in this universe can be understood at its most fundamental level without involving Planck's constant. And we're actually going to start talking about Planck's constant, I think, on Thursday. And there's a picture of Max Planck. Now, to get to that point, I want to talk about periodic motion with you. And periodic motion means something that repeats itself over a certain period of time. If the period of time is 24 hours, that's one day. That's your, diurnal circadian rhythm, right? Any kind of periodic motion is what we want to be ready for. And the simplest periodic system is a spring system. There's a picture of a spring for a car, for a suspension in a car. And if you've ever taken out the springs in your car, or you know what another set of springs is really, really strong and really tough to flex, is for a garage door. The springs at the top of a garage door that counterbalance it. Amazingly strong. Now, the force law for a spring depends on two things. First of all, the displacement from equilibrium position. All right, so if you know if you know how far the string is stretched when you just lay it on the table and you're not pulling it or pushing. What was that? What was that? That was from over there, right?
No, that was your microphone. Yeah, it was a microphone.
It was me?
Yeah.
Maybe it was my phone.
No, it was.
I know, I need it.
That was weird.
All right. Yeah, feedback, I guess. Oh, I know what it is. I didn't shave this morning. That's what it is. Anyway, so equilibrium. So the equilibrium position of a spring is, how long would the spring be if you just let it sit there, not stretching it, not trying to compress it, you just let it set. That's the equilibrium length. Okay, so now displacement from that by squishing it inward with compression or by elongating it with extension, that would be displacement away from equilibrium. And then the second thing is it's proportional to x, the displacement, and the more displacement, the more pullback you get from the spring. So, and hopefully that makes sense to you. If, common sense, the more you press a spring, the harder it fights back, or the more you elongate the spring, the more it pulls back. All right, and that's what item A is. The other thing is, it's a spring force is a restoring force. In other words, see, that's what I heard.
No.
It was like Darth Vader or something. Like it was.
Darth Vader. I'll have to listen to it on the podcast. Anyways, restoring force means it's trying to pull back towards equilibrium or push out to equilibrium. And so it's always opposite the displacement. So if your displacement is to the right, the pullback is to the left, and vice versa. Now we're going to go through some examples here. The first one is this idea of proportional to x. And on this one, first of all, let's distinguish the equilibrium position. So on this sketch here that I've got up here, I have a spring attached to a kind of reddish block. All right. And let's say that that at this position, the spring is completely relaxed. It's neither stretched nor compressed. So we would say that at this position, it's at equilibrium. And let's call that 0 in our x-axis. Just for it makes our bookkeeping a little bit easier. If your equilibrium is at 0, then the displacement is either a positive or a negative number. Positive for rightward, negative for leftward. That's nice, right? But if the object is actually at 0, then there's no force on it because it's proportional to the displacement. If your displacement is 0, 22 times 0 is 0. Anything times 0 is 0. All right, so at this position, there's no push or pull from the spring. Now, if you're over to the right or over to the left, you're going to get some pull. But at this position, no. All right? So that's part A. Now, 2A. And now let's do 2B, the restoring force. Now, this is where we're going to tackle the directionality if you're away from equilibrium. Okay, part A was about at equilibrium, 0 centimeters. Now, so if you're, for instance, out to the right, like this one is down here in the lower picture, the lower sketch, now here's my x position, and x would be like, positive 1.4 centimeters or something like that. If you're out there to the right, that means the spring force is back the other direction. So draw in a leftward arrow to represent the spring force when it's at that position x. If x is out there to the right, the pull force is to the left. It's pulling back. All right. Now, by the same token, and this one doesn't have a picture on this page, if x is left of the equilibrium, so down there to the left of 0 in the negatives, then the push force is rightward. The spring force is rightward. The spring is pushing you back towards equilibrium. No matter where you go, if you leave equilibrium, the spring is trying to restore you back to equilibrium. And because of that, this will oscillate left and right if there's no friction. Oscillate means to wiggle, to go back and forth. And usually it means in a periodic, regular manner. Okay, here's a sketch of a different weight, a hexagonal weight. And there's a kind of a schematic picture of a spring, bunch of squiggles. And in this one, the hexagonal mass M is to the left of equilibrium. So I want to think about this one, and I'm going to ask you some questions now about the position and the spring force for this configuration of a spring mass system. So the spring is symbolized by the letter K, and that letter K is called the spring constant, and it basically encodes the property of the spring that you would maybe call the stiffness, how easy or how hard it is to stretch or to compress or to twist. All right, so here's a question, and this is a clicker question. You can jot down the basic question and then jot down your answer. If the equilibrium position is officially at x equals 0.0 centimeters, as we've been doing, then the position of this hexagonal mass, what will it be? A, B, or C? And go ahead and jot this down in your notes. Jot down your answer along with your sketch. So you could write down, e.g., the position of this mass is, and then A, B, or C. How many of you voted for A? How many of you voted for B? Okay, so that means everybody else voted for C. Or some of you didn't vote. But here's the answer, B. And the reason for that is it's to the left of equilibrium. Equilibrium is 0.0 on the x-axis. So if you're over here to the left, that means give it a negative number. You know, like negative 2.4. Okay? Next clicker question. Let's to the left of equilibrium. Okay, to the left. Everything in an oscillating system like this, Camille, all your positions and displacements are always relative to the equilibrium position or the equilibrium configuration. So that's what you got to keep in mind. So when I say left, what I really mean is left of equilibrium. Kane. I could, but then you just got to, so if I say equilibrium is at 1.2 centimeters, then you just got to subtract. But, most of the time we just call it 0. What would change K? Mm-hmm. Yeah, I'll talk about that in just a minute. All right, another question. Somebody had a question over here? Good. All right, let's keep going. Next one. All right, let's say it's at position negative 2.4 centimeters. All right, that's good. Left of equilibrium, Isabel. So that's good. Negative 2.4. All right, now, what is the spring force going to be? Is it going to be leftward or rightward? If it's leftward, oh, this is the typo that I forgot to change. There's actually two good answers here. Left word or right word? Positive number or negative number? Independent decisions or independent descriptions. All right. Raise your hand if you voted for D. Okay, good. And actually, B is also correct too. That one was supposed to be a negative 1.21 and a negative. That's a Dr. B typo, so it's actually a good thing we're not doing clicker questions. But from this, I want you to understand now the following force law. Here is the force law for a spring. F equals minus kx. And David, this is way, way, way simpler than universal gravitation. You know, G, M1, M2 over R squared. What? That's very tricky to work with. This is a walk in the park. Yep, K is called, here we go. Here's my next slide. K is called the spring constant. It encodes the stiffness or the stretchiness of a spring. And in general, any kind of a physical interaction will have a small part of its range of motion in which it behaves like a spring system. Now, gravitation is a 1 over r squared force, but there are situations where you have a stable orbit and you can produce oscillations in which it acts like a spring. Now, SPE, that's the spring potential energy. All right? So when we talk about the potential energy of gravity minus mgy, yeah, that's for gravity. For a spring system, the formula is 1/2 kx squared. Now, if you've had calculus, you may say to yourself, "Ooh, Dr. B, that looks like an integral," and it is. There's a bunch of calculus, not that fancy, but there's some calculus. So I'm not going to show you exactly why you go from f equals minus kx to SPE equals 1/2 kx squared. But we are going to use 1/2 kx squared to think with, and that is the formula for spring potential energy. Elizabeth. What is the law called for what? That's the spring force law. All right. Another question, Abigail, did you have a question? Okay. Any other questions? All right. Now, about the spring constant. The spring constant is the property of a spring, not of a substance, but of the design of a spring. So you can make a steel spring that has different stretchiness values, different stiffness values, depending on how thick the wire is, what the radius of turning is, stuff like that, how they treat it. So for instance, this set of springs over here on the left, that's something that you would use in an automobile. So I think this is a set of springs and shocks for somebody that wants to lower or raise their car, I guess. Okay, and if you've ever looked at the springs in a car, they're really stiff. Now the second one over here, it's a blow up of something that's actually pretty small, 0.3 inch diameter. Okay, so that's way smaller than your finger, and smaller than the smallest fingernail on your smallest finger, your pinky. All right? So 0.3 of an inch. So that spring is really small. Now, what does the spring constant have to do with both? Well, the spring constant of the ones over here, the red ones on the left, is going to be pretty big. And my wonderful students, the units of measurement for the spring constant are newtons per meter. K is measured in newtons per meter. And what that means is, if it's a strong, tough spring, you'll only get a few newtons per, or it'll require a lot of newtons to squish it down by 1 meter. So newtons per meter will be a big number for a stiff spring. But if you have a really easy spring like the one on the right, see the one on the right is like a spring you might find in a toy or like electronics. Any kind of electronics or toy that has a button that clicks on and then clicks off, it's got a spring in it. And if it's a toy, it's got to be a spring that's easy enough for a little shrimpy kid to push it. Okay? So it can't have a, so 1 meter doesn't take many newtons, right? 1 meter squish down. Even though you might just squish it down by a millimeter, you can still get, you can still figure out the rating in newtons per meter. And so for some springs, it's got to be small, so a little shrimpy kid can operate it. Other systems, other springs like the ones on the left, it's got to be ginormous because you're trying to support a car, a ton or more. And just think about those big trucks out on the highway, the big 18-wheelers. They're carrying tons of stuff, so they got to have really stiff springs for those babies. And think about, here's another one. Airplane, a jet. That's a lot of mass. And they've got to have good springs for that. Now, so that's the spring constant, K. And that's the only parameter of a spring that you measure. You design your spring and then you measure it. Or hopefully you design your spring so that it can have the spring constant that you need for your application. The reason this is important is because anytime you see a force that's a minus kx type force, in other words, it's depending on some spatial displacement. It could be more force depending, how far you go in the x direction. Or even, sometimes how much you twist it. So the twist angle could be the coordinate for a spring force. All right? Anytime you see a spring force that's proportional to the displacement, or anytime you see a potential energy that's proportional to the square of a coordinate, so 1/2 kx squared, then it's going to oscillate. It's going to oscillate no matter what you do. All right? And that's important for all kinds of systems. And that's why it's important what I said earlier, that every physical interaction in the universe is going to have a small regime, a small physical domain in which it does behave just like this, very closely to what a spring does. And for that reason, understanding spring oscillations is incredibly powerful for understanding every physical interaction in the universe. Matter of fact, for understanding quantum systems. Now, another term that I want to go over with you before we dismiss is the topic of amplitude. Amplitude. Now, I'm going to explain it to you in terms of this picture, A, B, C, and D. It shows a spring mass system with kind of a yellowish-orange mass attached to a spring. And in picture A, the spring is, or the mass is at the equilibrium. And then in picture B, it's out at maximum extension. And then in picture C, it's like a snapshot. It's back at equilibrium, but it's heading to the left. It's heading left. And in picture D, it's all the way compressed. It's at maximum compression to the left. And after that, it's going to start rotating back out to the right and hit equilibrium again, start it all over again. So one full cycle in this diagram for us, I want you to think of a full cycle of motion. Shuttling back and forth. Can be oscillating like this, left and right, left and right, left and right. And that's what springs do. And if there's no friction, it'll just keep oscillating for a long time. I want you to think of it as 4 journeys to or from equilibrium. So here's the first part of the journey. From equilibrium out to maximum extension. All right, so here's maximum extension out here at the end of, or at the far right of sketch B. So these are like 4 snapshots. All right. So from equilibrium, it moves out to max extension. And then it stops for that instant only. And then it starts accelerating back to the left. And here's the next part of the journey. From max extension back to equilibrium. Okay? Now, on a spring system like this, if there's not a lot of friction on the tabletop, it's going to overshoot. All right? So it gets to equilibrium, and then it keeps going. What? Yeah. It's going to overshoot equilibrium. It's going to have enough kinetic energy to battle it out past equilibrium and keep going and eventually slow down at max compression. That's right here. At max compression, the energy in the system is all potential and 0 kinetic. At that position, it has come to a stop. And it turns around, and one more journey from max compression back to equilibrium. And now you start the motion again. Kane.
So once it gets in D where it's always pressed, it's still gonna overshoot equilibrium.
It's going to shoot equilibrium again, but this time on the way out to the right.
Yeah, and it's gonna keep doing that until it's back to equilibrium. Right?
Yeah, you get to equilibrium, but once you're there, you start to overshoot, and you overshoot all the way out to max extension, and then that sends you back to the equilibrium, but you overshoot, and you overshoot all the way to max compression on the left, and then that sends you back to the right, back to equilibrium, and you overshoot it. So you keep overshooting if there's no friction.
Full compression always shoots you out to the max.
If you're compressed, you're on the left. That means the force is back to the right. All right. So that's one full cycle. Now let's make a couple notes here. So adding up all those 4 journeys gives you one full cycle. Right. And so you can think of it, a full cycle, as 4 journeys either to or from the turning points, to or from equilibrium. Now, for reasons of laziness that mathematicians and scientists try to retain, and after doing a bunch of trig and calculus, we found that using the amplitude in other words, the size of one of these 4 arrows, any of them, that's the most convenient number or quantity to express the size of a wave. So in other words, you don't, if you're doing calculus and a little bit of trig, you figure out, okay, let's not use the full left to right variation. Let's just use half of it. And then all my symbols are nice and everything looks nice and stuff. It calculates out nicely. And that's what's called the amplitude. The distance of variation from equilibrium out to one of the turning points. either the max compression over here on the left or max extension over there on the right. Or if you think about waves in the ocean, let's look at this. Here's kind of a side view of some waves in the ocean. Sea level's right through the middle here. All right? Here's your calm sea. And a wave in the ocean, you're up here at the top of one of the waves. That's where the surfer starts anyways. And then in between each of the two crests, three crests, there's a trough. And the trough is below sea level. If you think about it. And the crest is above sea level. And the distance from sea level to the crest is the amplitude. Right, now here's another picture. The distance from sea level down to the bottom of the trough, if the waves are symmetric, and in the ocean they're frequently pretty symmetric. That's the amplitude too. Right? Now we could just as easily use the total vertical, but it turns out that for various mathematical reasons, half that size is the best number to use. Now, final comment before we dismiss. I'll bring you back to something that's very special about the electromagnetic field. Turns out that the energy pouring through a surface, from sunlight, per second is proportional to the square of the amplitude. And that is why the electromagnetic field intrinsically oscillates. And that is why Wi-Fi and everything else works. All the radio systems work on oscillation. All right. It's time to dismiss. There'll be some homework tonight, maybe sometime after supper. All right, so you have the rest of the afternoon off. Come up to the front after supper. If you have to, okay, good. I'll take care. If you need your printouts, come up here to the front. Thanks.